So what we're going to do now is we're going to talk about the second example of data abstraction implementation in C++. If you recall the one we talked about yesterday, this was the first one, and this one used a stack of ints, and we showed how we could hide the information so you couldn't access the private parts. We could have multiple objects that were properly initialized. The destructors and constructors were called automatically, and all that was good. But then I talked about the fact that the error handling was still obtrusive, and we're not going to fix that today. We'll fix that probably tomorrow or maybe next week. We also talked about how things were limited to one type, the int. We're not going to fix that today except by sort of a type def hack, which I'll show you in a second. But we will talk about that definitely starting tomorrow. And then I also talked about the fact that there was unnecessary function call overhead. And so someone asked about that. So the example we're going to look at now is going to fix that particular problem. And it's also going to demonstrate some interesting other issues that we'll have to think about with respect to writing robust code. And that'll be a foreshadowing for the topics we're going to cover starting tomorrow and continuing on to next week. So let me go ahead and share my IDE, and let's open up the right project. This is Data Abstraction version 3B. And as always, this is available in my GitHub repository. So this example looks a little bit like the one we did yesterday, although I've heavily instrumented it. And I've also changed the use of the type that the stack is working on. Yesterday's stack was a stack of int, and today's stack is going to be a stack of simple string. Now, we've already talked just a bit about simple string. We're going to look at it more now. But you can see up here, I type def T to be simple string. This, again, is not the best way to do it. It's just the way we're doing it to not have to talk about templates too much yet. But never fear, we will talk about templates shortly, starting tomorrow. And you'll see a much better way to do this. But this is good enough for our purposes at the moment. Now, this particular implementation is also going to introduce the rule of 5. And I'm going to start talking about it today, and then we're going to cover it in much more detail over the next few sessions, because it's a very sophisticated topic. Once you get your head around it, it's not too hard, but at first glance, you're like, what the heck is going on? And the rule of 5, which you can read about here at this link, is all about optimizing value semantics, which are so important for C++ and the C++ standard template library. And we're also going to talk about how we have a little optimization here for the push operation that uses these semantics. So if you take a look at the interface for this stack, it looks very similar to the one we looked at yesterday with just a couple of minor exceptions, but we're not using exceptions yet, but a couple minor differences. One of which is we have this alternative initialization constructor, and this is what's called the move constructor, and that is in contrast to this constructor, which is the copy constructor. So we've talked about copy constructor. Now we're going to talk a bit about the move constructor. And then you'll also see, if you look at the assignment operators, here's the classic copy assignment operator. And then here is what's called the move assignment operator. And both the move assignment operator and the move constructor have this really funky syntax with 2 ampersands. And that's what's called an rvalue reference, which is a very mysterious concept when you're first introduced to it. But when you break it down, it's pretty straightforward. And we're going to use this as a way to be able to transfer ownership of the parameters passed to the move constructor and the move assignment operator in such a way that will be very efficient, because we don't actually have to make a copy. And so that's the whole point of the move stuff, is it's an optimization for transferring ownership. And we'll take a deeper look at why we need to do that. Now, let's go back to the main program. Knowing that this works now with a stack of simple strings, you can see what we're going to do here. And I've deliberately kept our stack very small so you can see exactly what's going on here. So we're going to define a couple of stacks. One is S1, and that's going to have an element of size 1. It's going to have one element in the stack. And then the second one is S2, which is going to start out initially with no elements at all. And you can see that I do a little print statement here to say we're starting the constructor, we're ending the constructor. And you'll see why we need to do that, because you'll be able to identify the differences in the behavior in the code. What we then do is we go ahead, and while the stack isn't full, which it it'll be full pretty fast because there's room for one item. We're going to go ahead and we're going to create a simple string. And then we're going to go ahead and push that simple string onto the stack. And you'll see if you take a look at what method is called in this particular case, it's going to be this one right here. Okay, so let's go back over here. And then what we're going to see is we're going to, the way we do this is we create a string that's going to take the number passed to it and convert that into a string. So we're going to convert the number 0 into a string 0. And then we're going to get the C string for that. And then we're going to use that to create our simple string. And then we push it onto the stack. And you can see it uses the version of push, again, that is based on the copy, the pass by reference model here. So it's using a pass by reference approach, and it stores that item into the stack at the current top location. Okay, so then down here, we're going to see that after we do that, we're going to go ahead and pop the item off of the stack. So the stack is now going to be empty, and we're going to print the top item and then pop it. Okay, so that's one thing. The next thing we're going to do is now we're going to show the use of a different push operation, and this is the one that takes the rvalue reference. So it's a t ref. It sounds like a dog, ref. And in this case, notice unlike the version here where we created an explicit string and then pushed it, in this case, we're going to go ahead and push basically a temporary. And that figures in to be very important in terms of the optimization that's going to be performed here. So this push operation is actually going to end up being this method. And this method uses what's called move semantics. So what it's going to do is it's actually going to take the contents that's passed into it, which in this case is a temporary, and it's simply going to move the contents using the assignment operator, the move assignment operator. It's going to move it into this location. And you'll see that that's going to be a lot lighter weight because it doesn't actually have to make a copy. It just borrows the contents of what is passed to it. So we're passing it a temporary, and then the move operation is just going to take the contents of the temporary and slam it into the object that we're assigning to, and then the temporary will just evaporate and nothing will be done to it because we've stolen its innards, and you'll see how that works. So that's what move semantics are all about. They're about transferring ownership from the right-hand side of either an initialization or an assignment to the left-hand side. And then we're going to go ahead and use the copy constructor in order to make a copy of stack S1, which now has one element in it. And then we're going to go ahead and we're going to use, and we're going to put that into a new stack called S3. And then we're going to go ahead and move the contents of stack S3 into stack S4 using the move constructor. And this is going to allow us to again, do this clever ownership transfer that's going to steal the innards of S3 and move it over into S4. Now you'll notice that when we do these kinds of things, we've actually mucked with the innards of S3. And so if down here we were to try to say, C out S3, let's see, probably have to do something to get its actual value since we don't have a print statement for that. So S3 dot top or whatever. You see the little highlight that's happening there? And it's warning us, it's saying, you're trying to use F3 after you scooped out its innards and left it a husk, an empty shell of an object. So that's the compiler trying to save us from doing something really stupid because we've removed and destroyed the contents of S3. Then the last couple things we do here is we show off the copy assignment operator, where we're going to take S1 and copy it to S2. And then the last thing we show here is we're going to do a move operation on S2 to move its contents to S3 using the move assignment operator. Once again, S2 will become an empty husk or an empty shell with no state left in it anymore. And then finally, we go ahead and we print out the contents of S1, which will just have one object in it, and it'll go ahead and print that out. Okay, so let's go ahead and run this code, and then we'll kind of break down and see what it's actually doing. Whoops. Didn't like something. Oh, probably have to rebuild this. Give me 1 second to go in and clear out the cache. Sometimes you have to go in. It's sort of frustrating, but actually this is probably a good thing to show you. CLion sometimes gets confused. Its caches get confused, and so you need to go in and do stuff like I'm about to do, which is pretty gross. All right, so we deleted all this stuff. Now we can come back over here, hopefully, and we'll go ahead and rebuild it with C++, overview, capabilities, data abstraction, 3B. So we want to import it. And hopefully it'll be happier this time. Should be. All right, let's try that again. Okay, all is well. And that was actually a fortuitous mistake, because that does happen from time to time, and you just have to know how to clear out the cache for CLion. If you ever run into this problem and your code is saying something like, can't find CMake project, that's probably what's happened. It's gotten out of sync. Okay, so here is what the code actually looks like when we run it and we get the output. And this is really instructive to show the differences between these different operations. So we start out, we say begin constructor. As you can see here, we're making a stack with one element. So that's going to go ahead and simply print out a default constructor. So we have an element in the stack that has no contents. And then we go ahead and we call the push operation. So that's this code here. And you can see that what we're doing is we're doing a full-blown copy. And if you look here, you can see that we first make ourselves a simple string. That's what this call is doing. And then we go ahead and are going to, I take it back. First we make a simple string here, and then we go ahead and have this used to assign to it. And then we call the push operation. And you can see here that what this is doing under the hood is it's going ahead and pushing this content into the object. So if you go and look at push here, you can see that what it's doing is it's assigning, so this is the assignment operator right here, it's assigning the item into the top item on the top element in the stack. And that's calling the assignment operator. And if we go here, hopefully it's smart enough to take us there. Nope, it's not smart enough to take us there. That's all right. We will go to simple string, and we will go look at the assignment operator. And here's the assignment operator. That's what's being called here. And you can see that that's what's printing out this helpful little message. And what it's doing is it's going to make a temporary copy of the right-hand side, which in this case was the string that we created here, the simple string we created here. It makes a copy of it with this constructor call. Then it calls swap. And swap, as you can see, is actually very much like your swap from programming assignment number 1, where it just swaps the contents of the fields. Swaps len and it swaps stir. That's what a simple string is implemented to have. Simple string is implemented to have a len, which keeps track of how big it is, and a char star, which is the string that it's going to be pointing to, that's been allocated dynamically by stir new. And so as you can see here, that's going to go ahead and do the swap. You can see the swap. And then we're going to get some destructors called, because we have to go ahead and destroy the object that we just swapped. So that'll go ahead and destroy the old object. And that's what we need to do for push. So you can see that there's a fair amount of code being done to push a simple string into our stack. And that's why I'm using my simple string, so we can annotate and instrument what's actually going on. All right, let's pop back over here now and keep going in the main program. Now we go ahead and we take a look at the top item on the stack, which you can see here, and we print it out. And now we're going to go ahead and do this version of push. And this version of push, as you can see, I mean, just look at the difference in the amount of code here. This is the version that we did before, where we're really passing it by constref, which ends up making an assignment inside. That's rather expensive. And here's the version that we're doing down here using this version of push. And this version of push is using the so-called move semantics in C++. So let's go ahead and take a look at that. As you can see here, what we're doing is we're taking this rvalue reference called rval. I probably should call it RHS again. But I'm going to go ahead and I'm going to move it. And move is this totally wacky, let's see if I can find that. May not want to find it for me. Oh well. Move is a very interesting little method in C++ that instructs the compiler to do move semantics on this code. And we'll take a look and see what move semantics mean in a second. And what move semantics mean is call the move assignment operator, not the copy assignment operator. So here is the move assignment operator. And you'll see that it's quite different from this assignment operator. This assignment operator is actually making a copy of the right-hand side and then swapping its innards with the left-hand side and then destroying the old left-hand side. That's what the copy assignment operator does. The move operator, in contrast, is just going to lobotomize the right-hand side. And what I mean by that is it's going to go in there, and assuming we're not doing self-assignment, it's going to go ahead and it's going to take the len from the right-hand side and make that rlen. Then it's going to delete the existing string because we're about to assign over top of it. So we need to delete it first, otherwise we'll have a memory leak. Then it goes ahead and it takes the string from the right-hand side, which is just a char star, and it assigns it to the left-hand side. It doesn't make a copy, whereas over here, this actually made a copy. And the reason it made a copy was it was calling this copy constructor, which was actually doing a stir new. This is the one that's the copy assignment. It's doing a stir new, and stir new, as you can see, is figuring out the length of the parameter, allocating a new array of characters of that length +1 for the null terminator, and then copying the contents from the right-hand side into the new object. So that's what's happening with the copy constructor. And what we want to have happen is we want to use move semantics. So we're skipping the copying, and instead we're just grabbing the pointer from the right-hand side and slamming it into the left-hand side after first deleting the left-hand side. And then here's the really twisted part. We're now going to set the right-hand side's string, or stir underscore char star, to be a null pointer. So what we've really done is we've transferred the ownership. It's like taking someone's brain and scooping it out and giving it to somebody else. Someone else may have a brain now, but the other person's lost their brain. So that's kind of what we're doing here when you do move semantics. You're transferring ownership. And the consequence of this is the code is way shorter. Number one, many fewer methods are being called. But even more important than that, we're actually not doing any copies. So move optimization avoids the need for copies altogether. And that is super duper cool. And obviously super duper efficient too. So let's go ahead and take a look. After we did this code, we pushed things on. Now we're going to go ahead and demonstrate copy constructor versus move constructor. And the differences are going to be even more radical for copy constructor versus move constructor. So as you see here, copy constructor takes our S1 stack, which we've just put one item into, and it's going to go ahead and make a copy, and it's going to assign it into the S3 stack. So if we were to go over to stack and we were to take a look here at stack, we would see that this is the copy constructor for stack. And you can see what it does is it makes a copy of the top item, puts it into the left-hand side, makes a copy of the size item from the right-hand side, puts it into the left-hand side, goes ahead and allocates a new array of type T, which in this case is simple string, that's big enough to hold all the contents in the right-hand side. And then it goes ahead and it copies from beginning to end the contents of the right-hand side into the newly allocated left-hand side. Now again, don't slavishly follow this code for your production software because it's deliberately got a bug in it, which we'll talk about when we talk about templates next time. But leaving that aside, let's assume for sake of argument that simple string won't blow up. And it won't for this example, but it's a danger you've got to be aware of. So we went ahead and made a copy, and you can see the copy constructor does not a lot of work, but for one simple thing, for a stack element with one item in it, it has to do all of this work. So it's going to go ahead and make the simple string, make an assignment of this thing, create a temporary, swap the temporary with the current item that was created by the default constructor, and then delete stuff. So fairly expensive, right? Now let's go ahead and take a look. And there was, by the way, there was one element in our stack. If we'd had 100 elements in our stack, that sequence would have been repeated 100 times. Now let's go ahead and see what happens when we use the move constructor. And the move constructor is going to end up calling this code here. Here's the move constructor. And very much like the move assignment operator, this is super duper stripped down. In fact, it's so stripped down that there's actually no real overhead here at all, other than just copying the fields and the pointer. You can see that unlike the copy constructor, which had to do stuff that involved the element we were dealing with, the simple string, there is no overhead here. And I mean, other than ridiculously insignificant overhead, like moving an integer from one place to another, or moving a pointer from one place to another. And that's exactly what we're doing here. Notice how we're copying the right-hand side's state, top, size, and stack, to the left-hand side, to the object we're initializing. And then we're lobotomizing the right-hand side. We're basically giving it a null pointer. So we're transferring ownership. We're moving its contents into the new object that we're creating here. So you can see here that that really has no overhead at all. And then we go down here and we do the same thing again with the copy assignment operator and the move assignment operator. And again, you can see the vast difference in behavior. So here's the copy assignment operator, which, as you can see, is going to make a copy, like we've talked about before. It's very similar for the copy constructor, except the copy assignment operator has even more work to do because it's got to clean up the left-hand side. So here's the assignment operator, the copy assignment operator. And as you can see, it's got some nasty bugs, but ignore those for the moment. We'll fix them shortly. But this, assuming no exceptions get thrown, this code will work and it will not leak memory unless an exception is thrown. But let's assume an exception is not thrown. What this does is it goes ahead and makes a new temporary object that's big enough to hold the right-hand side, copies the contents of the right-hand side into the new temporary object, deletes the old left-hand side, the stack pointer there, and then assigns temp to that stack pointer. And you can see that that code down here will end up doing all of these kinds of things in the context of the simple string and other stuff. In contrast, look at how ridiculously efficient the move assignment operator is. Again, it's got like zero overhead. So here's the move assignment operator, or not zero overhead, but very, very, very little overhead. Here's the move assignment operator. Much like the move assignment operator for the simple string, what it does is it basically passes the elements over from the right-hand side to the new, to the updated left-hand side. Before, of course, it has to delete the left-hand side stack, which we do here. And then it goes ahead and just assigns stack to be the right-hand side and nulls out the, whoops, that looks like a bug. That should be RHS. There we go, that looks better. And so then that goes ahead and transfers the ownership and nulls out the right-hand side. So very, very lightweight. By the way, I want to mention one thing because we had some good questions in office hours today about this. Whenever you allocate something with new, for example, you can see up here, we allocated new array of T. Whenever you allocate an array of something, you have to make sure when you free it up that you use the delete operation with the open close square brackets. Otherwise, you'll get the wrong delete operator called. You'll get the operator delete called to allocate one object, not an array of objects. And if you try to do that with your assignment number one, you'll get a weird error. It'll throw an exception and say something like, you can't do this. And that's why, because you need to make sure you delete things. If you allocate it as an array, you have to delete it as an array using this type of syntax. Okay, so that is just kind of illustrating how the MoveAssignment operator works. And then the final thing we do here is we go through and we print the results out. And then when we're done, destructors get called to clean up what's left onto the stack. And that's all done in the destructor of stack. Okay, so that's a lot of stuff to try to absorb. We will cover this topic again, MoveAssignment operator and the move constructor and all these other things. We'll cover these things again in the future. So if this went whizzing by a little fast, don't worry. It's an advanced topic of C++, but it's a very important topic. And the reason why it's important is it demonstrates the rule of 5. So there are now 5 methods. There are 5 methods. That's not 5, that's 5. There are now 5 methods that you have to be prepared to implement if you want to write code that's going to be fully abstracted and optimized in C++. And those 5 methods are the copy constructor, the move constructor, the CopyAssignment operator, the MoveAssignment operator, and of course the destructor. And we'll talk in more detail later about what things like no except means. That's basically a directive to the compiler saying this code does not throw an exception. And of course this code does not throw an exception because none of the operations here should be throwing exceptions. Destructor should not be throwing exceptions, and assigning one thing, assigning a scalar to another scalar or assigning a pointer to another pointer of the same type, that won't throw an exception. So we can mark this as no except. And the move assignment operator and the move constructor should always be no except style semantics. And we'll talk about those kinds of things a little bit later.